Welcome to this webinar. This is the first of 3 webinars on structural design through EC8 for seismic engineering in buildings. We are now doing a brief introduction where we will discuss some relevant topics in order to address the choices we will make during the webinar. The first question is, in structural models, how are we going to create them? What options do we have? Are we going to use 2D models or 3D models? This is also an important question. For example, 2D models, what advantages do they offer? Well, some, such as they can be quite simple models for example, nonlinear analysis and for performing time history or pushover analyses. However, there are some restrictions. The buildings must be regular in plan. The seismic responses must be independent and decoupled in the principal orthogonal directions. We are required to have 2 independent models for each horizontal direction. There is additional work in combining the results of both models in the 2 main directions, and this is clearly not very convenient or practical. On the other hand, 3D models are much more effective in representing the dynamic behavior of general 3-dimensional structures. In fact, we may need to use a 3D model to verify whether we meet the conditions for performing 2D analysis. Post-processing is much simpler if we have a single 3-dimensional structure, because we do not need to combine forces from different models in 2 different directions. There are important aspects. Normally, with 3D models, there is a temptation to include all elements such as slabs and walls using shell elements. When we do this, we need to exercise additional care to ensure that the load path control for gravity loads is done correctly, because the stiffnesses of beam elements and slabs will start to fight each other. Therefore, we must know exactly how we are allowing the gravity loads and other loads to be distributed according to the stiffness of the elements. And finally, 3D models can be applied to any type of structure and geometric configuration. Another question is, linear or nonlinear models? What models do we use, and in which situations? Why nonlinear models? Today, many people raise a lot of questions about nonlinear analyses, and we see that, more and more, the trend is for structural engineers to start performing more situations with nonlinear structural analysis. Typical examples of why to use nonlinear analysis. Starting with, if we want to assess the seismic performance of a new building, to confirm the plastic mechanisms and their distribution, and the size of the damage. If we want to assess an existing structure or one that is going to be strengthened, a building with retrofitting. Or to evaluate buildings whose design was not done according to EC8 or according to the capacity design rules in EC8. In general, when we are doing this type of structural strengthening, designing according to EC8 but using nonlinear analyses leads to a much better cost-efficiency relationship. We could use pushover analysis to review the overstrength factor, which is used to enlarge or increase the behavior factor due to structural redundancy. We could also design buildings using deformation-based methods, instead of force-based methods. We could also design structures that have base isolation. In all these cases, linear analyses are only allowed with significant restrictions, and only in very particular cases could linear analysis be used. What other situations do we know that can significantly limit our linear analyses? Well, if we have considerable p-delta effects in the structure, or theta values greater than 0.2. Slender bracings whose behavior cannot be characterized by linear analysis. If we have foundation uplift, soil structure interaction in basement walls, pounding between adjacent buildings, which would need to be evaluated in nonlinear time history analysis with contact. And finally, precast components that rely on friction and contact behavior. We must also provide some very clear ideas about the types of considerations we must make when performing nonlinear calculations. First, nonlinear analysis consumes much more time and patience. Each problem is a different problem. We should always start with very simple models, preferably linear ones. Clearly define a lower and upper range of expected results, and preferably ensure that our initial nonlinear models are quite small and can be calculated fairly quickly. Keep in mind that small changes in properties, dimensions, or loads can generate disproportionate results, an example being nonlinear responses. And on the other hand, It is important to consider that we must always perform a sensitivity analysis and understand that we are no longer within the concept of linear amplification of load factors through load combinations and partial factors. It is now our responsibility to determine the statistical uncertainty of which types of variables and loads we must define. Some simple considerations for linear analysis. Even if we need to perform nonlinear calculations, we should always use a linear analysis. In some cases, there are even restrictions on what possibilities we have for using nonlinear analyses to guide the total behavior or resistance of the structure according to the results we obtain from the response spectrum analysis. As mentioned earlier, linear analyses can be very important for defining an upper and lower bound of stiffness and results so that we can have some level of confidence in our nonlinear model. And on the other hand, it is also very important that when we use linear methods, meaning when we analyze linearly, this does not imply that the response we obtain, the seismic response, is linearly elastic. There are other topics, details, and variables that we introduce into this calculation, such as the behavior factor that is used to modify the elastic seismic spectrum, and many other rules that Eurocode 8 imposes for the structure to have a ductile behavior and allow us to amplify our behavior factor. In this webinar, we will focus on linear analyses and three-dimensional models. We will be using ETABS most of the time, but SAP 2000 in 80% of situations has the same capabilities in the same way. Regarding the linear methods that we are going to use, the types of linear methods for seismic analysis include the equivalent lateral force method, in which the response depends largely on the first translational modes of the structure in each direction. There is a restriction that the fundamental period of the structure must be less than 2 seconds and less than 4 times the value of Tc, which is the upper limit of constant acceleration in the spectrum. And the structure must be regular in elevation. On the other hand, we have another method such as the response spectrum modal analysis, which provides a statistical prediction of the maximum magnitudes of different modal quantities. It is the reference method recognized by Eurocode 8, applicable to all types of structures, and the most widely used tool for seismic structural design worldwide. In general, we obtain design forces that lead to better seismic capacity or performance compared to the equivalent static linear force method. This linear method or these linear methods depend significantly on two very important concepts in seismic analysis. One of the concepts is the ductility classes. In this webinar, we will assume the medium ductility class, which is what we will use in our models. And the other very important aspect is the behavior factor, which will also significantly influence the final result. Regarding ductility classes, the lowest class can only be used in zones of very low seismicity. Its behavior factor must be below 1.5, and the structure may even be designed only with Eurocode 2 rules. On the other hand, medium and high ductility classes result in buildings with a much better cost to seismic performance ratio in moderate or high seismic zones. We can observe during the design that we are dynamically exchanging ductility and dissipative capacity for strength. That is, for behavior factors greater than 1.5, this is exactly what we are doing. The design must rigorously comply with the provisions of Eurocode 8 because this is crucial to ensure the required structural ductility. And in the case of high ductility, the design provisions are much more demanding than in medium ductility, and in this case, high ductility buildings can have much higher behavior factors. In general, extensive conformity, checking, and quality control procedures are used during construction if we are in the higher ductility classes. That is, there are many aspects of design but also of construction quality and construction control. On the other hand, the behavior factor we are going to calculate is a limit value that depends significantly on several properties: the ductility class, as we have seen, the type of structural system, regularity and height, the aspect ratios of the walls which affect the kW factor, the overstrength factor, the alpha U over alpha 1 ratio, and also the regularity and plan, which only applies when we are in the approximate domain of alpha U over alpha 1. A structure can have different behavior factors in the two different directions, unless the structure is an inverted pendulum or a torsionally flexible structure. The question now is how all these concepts are used in our design. Let's look at a small flowchart. This flowchart indicates the path we will have to take during this webinar session, because the objective is to reach the end of the first session with a well-defined and clear calculation of the behavior factor, as well as a clear idea of whether the distinction between primary structure and secondary structure is valid. The 5 different types of structural systems recommended by Eurocode 8 are a frame system or mixed frame system, a coupled wall system or uncoupled mixed wall system, a coupled wall system or mixed coupled wall system, a torsionally flexible system, and an inverted pendulum. After this structural classification phase, there is a set of other steps we must take: checks for regularity and height, calculation of a kW factor, which is a very simple calculation, and checks to verify if the structure is regular in plan, which also occurs during the calculation of a factor called alpha U over alpha 1. There is a whole set of procedures that we will have to perform in conjunction with our structural models until we simply arrive at a behavior factor value and a conclusion as to whether it is truly possible to assume the relationship between primary and secondary structures. Regarding how we calculate these factors, the kW factor serves to potentially reduce the behavior factor, especially if the walls are not ductile. That is, they lack ductility. We will look at this calculation in more detail, but it is well defined in the Eurocode. The other factor, alpha U over alpha 1, allows for an amplification of the behavior factor. We will also clarify this during our webinar, but the maximum and minimum factors that can be applied are very clear when consulting Eurocode 8. So, quickly, to give everyone a clear idea, after this introduction, what we propose to do during this webinar is, first, make an assumption of primary and secondary structures and configure different stiffness models in our ETABS application. We will develop the necessary processes to check if we are in an inverted pendulum situation, check if it is a torsionally flexible structure, and classify our structural system in the 2 principal horizontal directions. We will also calculate the kW factor for both directions and the alpha U over alpha 1 factor for both directions, including the check for regularity in plan and height. At the end of this webinar, we will verify the contribution of the secondary elements and whether this contribution violates any of the conditions imposed by Eurocode 8. Now, we will start by looking at and getting to know our structural model. Let's begin by getting to know our building. Initially, I want to tell you that the building is available for consultation at 2 different moments, 2 different versions, an initial version before defining the properties and another version resulting from this session. Our building is a C4050 concrete structure, with B500 rebar. In plan, we have dimensions of 34 by 20 meters with 12 stories. Our slabs are waffle slabs with a 30 centimeters total depth and a 10 centimeters compression layer. We have perimeter beams of 30 by 80, except for the beam on the right facade, which is 30 by 100, and a roof perimeter beam which is also 30 by 100. All central columns are square and have a reduction in dimensions from 600 by 600 down to 30 by 30 at the roof. We have 3 30 by 80 end columns on all floors, and the facade column connected to the 30 by 100 beam is also 30 by 100. As for the walls we have in our building generally have a thickness of 30 centimeters. And we have 3 specific wall zones in our model. In the left zone, 2 walls with a 3-meter length are coupled by beams with a 1.2-meter depth and a 3-meter span. In the central zone, we have a C-shape coupled with 2 walls by beams. And finally, on the right side, we have a wall with a length of 7.4 meters, which makes this structure more asymmetrical. Now we will talk about a decision we have already made, which is the distinction between primary and secondary structures. We made a choice. The primary structure considered corresponds to all walls and all perimeter frames of the structure. It is necessary and very important to know that the consideration of being a primary structure depends heavily on the direction. In other words, in different directions, a frame may be primary in one direction and secondary in the other. Frames and walls are primary structures when they are bending about their major axis, highest inertia. In the opposite direction, we have a secondary structure. Naturally, all other elements, the central columns and the waffle slabs, and their connections to columns, are considered a secondary structure regardless of the direction. Regarding the loads applied to this building, in summary, it is a building with live loads considered for Category B, so, for offices, with a live load of 3 kilonewtons per square meter on all floors except the roof, which has a value of 1 kilonewton per square meter, non-accessible roof. For the remaining dead loads, we have 2.5 kilonewtons per square meter on all floors except the roof. On the roof, we considered 2 kilonewtons per square meter. We also considered facade loads and staircase loads. We can visualize the application of these loads on the staircases and facades. This summarizes the geometric characterization of the structure and the loads. We also have wind loads applied, but it is not important for this session to discuss their specific definition. Now regarding specific modeling aspects that are not visually apparent but are very important. We begin with end-length offsets. These are elements at the ends of column and beam members. This tool exists in CSI applications, ETABS, SAP 2000, and allows for the consideration of the intersection thickness at the column beam joint. This segment allows for a different stiffness consideration, and, on the other hand, ensures that the internal forces results are reported at the face of this segment, the outer face, and not inside the joint we are discussing. The implications of using an end-length offset affect the internal forces, since results are only reported up to the segment, and the stiffness of the element, which becomes slightly higher because we consider the segment to be totally or partially rigid. We opted to set 50% of the segment length as fully rigid. This precision is used because there are important aspects related to the building's stiffness. Since we are performing checks like interstory drifts, it is important to quantify these values as realistically or reasonably as possible. For example, when dealing with relative displacements between floors and we need to calculate numbers and values that are important to quantify, it is also important to quantify the stiffness of the elements in our frames as realistically as possible, or, rather, in a way that is somewhat relative or more reasonable. Another very important aspect is the insertion points for some columns. For ETABS to process checks like capacity design and other aspects involving the connection between beams and columns, it is important that the line model is connected and centered at the intersection points. In reality, we know that columns are not always perfectly aligned with the centers of beam intersections, so we must place them off-center using the end offsets or insertion points tools, which allow us to easily change their position. This influence is not only graphical and geometric, but it also affects the way the stiffness matrix is assembled at these joints. Therefore, this is an important choice we made in this model. Another very important aspect is the connection between the beams and the walls. Between the beams and the walls, there is a joint that shares the connection between the beam and its entry into the wall. This joint has a stiffness on the wall side that acts as if it were a torsional stiffness in the direction perpendicular to the plane of the wall. In other words, it is neither a typical plate behavior nor a membrane behavior. It is a membrane torsion. Unfortunately, this degree of freedom, called drilling, has a stiffness behavior that varies according to the size of the finite elements of the walls. Consequently, depending on the generation of the wall mesh, we would have a more rigid or less rigid connection in terms of the implicit spring in the connection with the beam. To overcome this problem, we're going to assume that the connection is totally rigid. To simulate this stiffness between the beam-to-wall connection, we define a vertical end length that is connected to the lower joint in the wall. When this segment tries to rotate, it has a shear stiffness that does not allow it to bend, making the rotation entirely dependent on the shear stiffness of the wall as well. This somehow simulates the rigid entry behavior of a beam into a wall. These are modeling details, but they are important ones. Another very important aspect to comment on is how the construction of the analyses for this model was conceived. With the concern of calculating the structure, we have to create submodels. Essentially, we have created 3 submodels. One of them has an objective that is not specifically related to seismic analysis, but rather to obtaining more suitable and correct results for permanent loads. The results of the staged construction process, building a model with, for example, 2 floors at a time, allow us to have results at the end of the model without spurious deformations that are unnecessary and that also produce spurious internal forces. Normally, we counteract this with larger effective areas for the columns, but we can do it directly in the application with a staged construction tool. What we do is simply ensure that at the end of the structure, we have a dead load case that basically starts from the previous nonlinear staged construction load case. The final internal forces we have from this load case are simply the gravity loads, the final permanent loads after the construction process. This is just one model that is not related to the seismic part. The other 2 are related to the seismic analysis. That is to say, we have 2 models. The first model we call the global model for seismic analysis. It is a model where, through stiffness modifiers, we set the entire structure to 50% stiffness. It does not matter if they are secondary elements or primary elements. All elements are set to 50% stiffness in accordance with what the Eurocode requires for reductions in bending and shear. This model serves to classify the structure, to check secondary elements, for example, punching shear, and, very importantly, to check the contribution of the secondary elements to see if we made a correct and possible definition between primary and secondary elements. In this structural phase, we have different section modifiers. That is what makes the difference in being able to apply the 50%. The other model is the one that represents the primary structure, which is the other model necessary in this process for structural verification. Here, we contain the primary elements with 50% stiffness, but the secondary elements have a stiffness of almost 0. With the exception of some walls that have a residual stiffness that is not quite as small as almost 0 but is still significantly reduced. The objective of this is to avoid strange problems or modes with very low frequencies in the modal analyses that would cause issues in the model. The idea is that with this model, using section modifiers, the primary structure works and resists the earthquake in shear and bending with 50% of its stiffness, while the secondary structure is almost non-existent in terms of strength and transfer of internal forces. Now, what we are going to do is enter one of the flowcharts to understand our next steps. One of the first things we are going to do is find out if the building is an inverted pendulum or not. According to the code, we will have to verify if at least the upper third of the building has less than 50% of the building's mass. If this condition is not met, it means we have more than 50% of the mass in the upper third, and it is an inverted pendulum. It is very important that the primary structure does not dissipate energy by depending solely on a single element at the base. If we imagine we had only one wall as a primary element, we would say it is almost certainly an inverted pendulum. To perform this check, we have to calculate masses and follow a set of Eurocode prescriptions. When we create combinations to calculate the seismic action with masses, we use the typical expressions of permanent loads plus psi2 multiplied by live loads. This is an aspect we are very used to applying in seismic combinations. On the other hand, when we are going to determine the inertial forces and the masses that contribute to those inertial forces, we must consider a slightly different combination, with a psi EI that is affected by a phi factor, which we will see how it works. According to the Eurocode, what is recommended is that this psi EI is phi times psi2. This phi factor we are looking at here has a tabulated value. In our case, it is 0.8. The final factor we are going to apply is 0.8 times 0.3. which is 0.24. This will be our combination factor for live load combinations in terms of mass. How are we going to do this? We are going to use a concept in ETABS called mass sources, and we can have more than one mass source case. For example, we could have different modal analysis cases with different mass sources. Let's look at the types of options we have in the mass sources. The first definition is basically to ensure that the masses can come directly from the masses and materials, and consequently from the elements, because they have an associated material and a volume associated with that material and element. An internal multiplication is performed to define the masses in the element and in the structure. We can also have additional masses, where we manually add masses to the joints. This is very simple, but we can add them manually, though we do not need to in our case. We could also specify masses based on load patterns, where we define the loads, in this case, a live load and the remaining dead loads, and apply the factors we had calculated. Regarding the live load, we are going to use the factor we calculated earlier, 0.24. We will place it here. Another option we are not going to use now is, for example, the possibility of adjusting the mass centroid to account for a mass eccentricity or different mass eccentricities for different analysis cases, according to certain design needs. For a particular structure, it might be important to consider different analysis types where we have masses with different eccentricities in each case and a statistical envelope of the results. This could address the lack of knowledge we have about where the masses are by defining different types of mass eccentricities. This is an option, but we will not use it in our case. For the sake of model simplicity, we can also choose whether or not to include lateral masses, restricting the masses assembled in the lateral, horizontal, or vertical directions. This can be very practical to, for example, reduce or restrict the number of modes we obtain. In our case, we are going to focus simply on the lateral masses. These would be the mass definitions. Right now, we can start running the model and calculating the structure so that it is possible to know exactly the masses that will be assembled throughout the model. At this point, we will check whether it is an inverted pendulum or not. What we are going to do is take a first step that we might consider unnecessary, but which is sometimes important to have. We ask ourselves, how can we be sure that the masses have been placed correctly in the structure? To calculate this in a very simple way, we can create a combination that corresponds to the mass combination we intend to calculate, obtain the base reaction results of this combination, and access our table of assembled masses for the entire model. By comparing those masses or summing the masses from the table with the total base reaction of the model, we can clearly understand how far or how close we are to the results we intend. What we are going to do now is exactly this combination that allows me to check the mass results. So, the mass we intentionally want to check is named combination check mass. Dead loads at 1.0, super dead loads at 1.0, and live loads at 0.24. We will not have to run it again because combinations do not actually need to be run. The results are simply pre-calculated underneath. And now, we are going to export a table of assembled masses in our model and then compare them with the total reactions. We can export the tables to Excel. Excel is a very practical tool for interacting with CSI products like SAP 2000 and ETABS. We are going to use this Excel table manipulation to quickly check whether it is an inverted pendulum or not. The first point is to look at the total base reactions. We are looking for the total forces in the vertical direction, the Z direction. We will check that the assembled masses correspond in some way to the force that would arise in this direction. Here we are summing the masses, and it makes no difference whether we sum the masses in the Y or X direction. We multiply by the value of gravitational acceleration. And, since they are in tons or kilograms, we divide by 1000 to compare them with kilonewtons. we arrive at a value that is practically the same. We can look at the difference, which is less than 1 per 1,000, a very small value that may be related to the precision of the acceleration values we entered or other small factors that justify this minimal difference. Therefore, the masses are correctly entered. This is the first important check we have done. Now, let's check if the upper third of the building contains more than 50% of the mass. We are going to sort the assembled masses by their height, the z-coordinate, and check the value for 1/3 of the total height of the building. This is basically the top 2/3. Starting from the top 2/3 up, we have to sum the masses. We find the 27.6 position and sum all the values from that point up through the entire height of the building. Yes, we will start summing all the elements. We can see the value of the total mass here. We are going to divide the total value by. Let's look at the difference exactly and see what percentage. This corresponds to 39%. Therefore, it means it is less than 50%. In other words, we are far from 50%, so we can verify that we do not have an inverted pendulum. On the other hand, it is important to state that the primary structure, as defined, has more than one base element to dissipate energy. So, since we have more than one base element and less than 50% of the mass in the upper third, it is not an inverted pendulum. After verifying the inverted pendulum criterion, we will now consider another hypothesis we need to eliminate: whether this structure is torsionally flexible or not. Before we start following the rules for checking torsional flexibility, we will briefly analyze some results from our modal analysis. But the modal analysis we performed was based on an initial structure with nominal stiffness, without any type of reductions. For this initial analysis, that is quite acceptable. Let's look at the vibration modes. Right now, we are looking at the first mode in plan. Using some perspective to perceive that this mode is clearly not a purely translational vibration mode. That is, it is translational, but it has some rotation or torsion. Let's also look at the next mode. It will surely have translations in a different direction, but some torsion as well. This initial analysis is important not only to check if the first modes are completely translational. The code, in some references, allows us to skip this check if the first modes are completely translational. Another very positive and necessary aspect is that when looking at the vibration modes, it becomes much easier to detect errors in the model or faults in stiffness assignments. For example, visualizing the modes is highly recommended and quite beneficial. To be sure, we can also look at some important tabulated factors, such as frequencies and periods. We will access a different area of the application to do this. We go to the tables and look at the analysis results, specific structural results for modal analysis, periods, frequencies, and modal participation. This is to see if the chosen modes adequately represent any type of numerical solution for the structure's deformed shape. In this table, we can see the periods in seconds. We also see the modal participation ratios, along with the cumulative participation in both directions. It is clear that we reach more than 90% in both directions, which is generally the target. As a rule of thumb, we recommend using 3 modes for each story. These typically represent translation in both directions and rotation about the vertical axis. Whether all these modes are actually required depends on the modal participation ratios that can be achieved. When analyzing the results, it is important to focus on the periods of the first 3 modes. We should note that the first modes already include torsion. Additionally, the frequency of the third mode is quite close to that of the second translational mode, meaning the two are not significantly separated. This closeness introduces a degree of uncertainty. For that reason, it is advisable to proceed with the check for a torsionally flexible system. And how are we going to do it? Let's look at a very simple slide. We have to check if a stiffness satisfies expression 4.1b of Eurocode 8 by comparing two parameters, Rx and Ls. The parameter Rx is basically the square root of the ratio between two important things, torsional stiffness and lateral stiffness. This is done for each floor and each direction independently. This means we need to understand what bending stiffness and torsional stiffness mean at each story. It means that when a story is subjected to a force, whether translational or rotational, the relative displacements occurring between that story and the story below help us quantify the stiffness of that story, reflecting exactly the stiffness of the elements helping to resist. On the other hand, we cannot forget that these elements in each story are fixed into the elements of the previous floor. All these elements, perhaps at the first floor with total fixation, have a maximum stiffness. Therefore, torsional and bending stiffness vary across stories. Even if a building had all identical floors, the story stiffness would tend to decrease as the height increases. Another important factor is the LS ratio, the polar radius of gyration of each story, measured relative to the center of mass, and the sum of the story's mass. These two factors are part of the expression we are checking. It tells us if the torsional stiffness capacity compared to the mass eccentricity. If this set of effects is strong enough to guarantee the structure is not very torsionally flexible. This is a fairly clear concept in the Eurocode. As software users and designers, what do we need to do to check this? We are going to verify and calculate the ratios. The torsional stiffness for each story. We will calculate the lateral stiffness for each story in both directions, the total mass of each story, and the polar moment of inertia about the center of mass for each story. We already did the building's own mass earlier, but we need the polar moment of inertia based on the masses and total mass of each story. These are the elements we will calculate next, and we will learn how to do it with the program. The first objective is to calculate the torsional and lateral stiffness for each story, which can be obtained in just a single step. We can do several things simultaneously to achieve these goals. To obtain these values, it will eventually be important to estimate and calculate the centers of stiffness for each story. ETABS includes an automatic tool that allows us to calculate the center of rigidity for each story. One important clarification is that this tool only works when rigid diaphragms are assigned to the stories. If the structure does not have rigid diaphragms but we still want to use the tool, we can temporarily assign them, run the center of rigidity calculation, and then remove the diaphragm property afterward. To understand how this calculation works, ETABS automatically applies a force per story in 3 independent load cases, covering all stories and all 3 directions. This means the number of load cases is 3 times the number of stories. These forces consist of 2 horizontal translational loads and 1 rotational load about the vertical axis. Although these loads could theoretically be applied at any point on the structure, the method applies them at the story center of mass. Determining the rotational stiffness for each story is straightforward because we can determine it from the relative rotations caused by the rotational load. Since a moment creates the same rotation regardless of where it is applied, the exact point of application is not important, as long as it is applied at the story level. However, when we apply a horizontal load, the point of application is not irrelevant when we are trying to determine the translational stiffness of that story. So how does the method identify the location of the stiffness centroid, or center of rigidity? Since the rotational stiffness of the story has already been determined, we can then apply a horizontal force at any point on that story. This horizontal force produces both a horizontal displacement and a rotation. By relating the obtained rotation to the previously calculated rotational stiffness, we can determine the eccentricity between the point of application and the true center of rigidity. This is the point where a horizontal force would produce no rotation. Using this methodology, ETABS determines the center of rigidity for each story, producing separate results for each direction and for each story. Once the centers of rigidity are known, calculating the translational stiffness of each story becomes straightforward. ETABS already provides the story drifts at the centers of mass for any lateral load case. Since we also know the exact locations of both the center of mass and the center of rigidity, we can use a simple expression to transfer these relative displacements from one point to the other. At first glance, this procedure may seem slightly complex, but in practice it is very easy to implement. By exporting the relevant ETABS tables to Excel, the calculations become simple and efficient. So, let us now return to the model and see how the centers of rigidity can be obtained automatically. and we are going to show you how it is possible to then obtain the centers of rigidity automatically. This option can be accessed in the Analysis menu through the Set Load Cases to Run form, which includes the Calculate Diaphragm Centers of Rigidity checkbox. We can update this, since rigid diaphragms have been defined, so the box must be checked for the calculation to run automatically. When we check it, several additional load cases will run, as mentioned before, but we are not going to see them here. That is, they are all invisible and internal load cases, and the program just performs them internally to discover the centers of rigidity, and at the end we access a table with the centers of rigidity for each story. Once again, I will mention that the algorithm is the one that was discussed earlier, and it can be consulted in the CSI wiki, but it is quite simple to understand. At this moment, the software is running the model. And it is done. We are going to look a bit at the obtained table of centers of rigidity. And we are going to see the table. And we are going to choose, in the structural output, the centers of mass and rigidity table. We have to assign a load case. And here we have the centers of mass, which are the columns we are going to select. And the centers of rigidity, these two now. These two columns for centers of rigidity. And why are we going to use this? The strategy is to export these tables, and, on the one hand, we will have the centers of rigidity properly calculated along with the displacements in each story, which later allows us to calculate the translational stiffnesses of each story. But also, while doing the calculations we are going to calculate, apply our initial loads at the top of the roof, applying them at the center, the forces at the center of rigidity. And we are going to memorize the coordinates of the top story of the roof, so that it is possible to apply the loads we are going to apply on the top story to serve as a force reference, so we can later have a force displacement relationship to obtain the stiffnesses. We are now going to continue with the next steps. We are going to create a joint in the structure, which is the joint where we are going to apply the forces used to measure the stiffness of each story. We are going to draw a point using the ETABS editing tools. We look at the created joint. And now we are going to change the coordinates according to the values we had memorized, so that it is possible to define the joint at the exact point of the center of rigidity, making it possible to apply the loads to the roof slab. At this moment we look at the joint. An important aspect is that we have to include this joint in the automatic meshing of the elements. It is very important that this property is assigned because this element should influence the mesh. It could be left without influencing it, and there would only be the possibility of simply being used to distribute loads. But for consistency reasons, for the exact application of the forces and to guarantee that there are no problems with mass undefinedness, it is appropriate in our cases to ensure that the newly added points have this property well defined. That is, to guarantee that this point participates in the automatically generated mesh. We observe that the point is also not at the geometric center of the structure, but it is shifted toward where we have more walls and greater stiffness. And on the other hand, that is, we clearly see that there is a plane asymmetry in this geometry. The next step is to create the load cases and apply the forces so that we can measure the stiffnesses of each story in terms of directions. Two orthogonal flexural directions and one torsional direction. We are going to create a load pattern called Fx, another called Fy, and another one called M, to apply a horizontal force in two directions and a torsional force. We select our joint, and we assign a load to that joint. In the case of M, we apply a value of 1 times 10 to the power of 6 kilonewton meters for numerical reasons. So we have good, significant numbers to accurately determine the stiffness. We are also going to do the same with the other two forces, Fx and Fy. We are going to use the same value, we already have it memorized, which is 1 times 10 to the power of 6. And this value is going to be applied in all three directions. And we have forces in the three directions. It is important to mention that the three forces are going to be applied to a crack structure. In the model, which is the model we consider to be one of the initially defined submodels, where we had three possibilities. The construction sequence possibility to calculate the dead load of the structure sequentially, the crack stiffness which was the global seismic model with the entire structure cracked at 50%, and the model with the primary elements. What we intend to do is classify the global structure. For now, we use the crack structure that has the entire primary and secondary structure at 50% stiffness. And therefore, each of these three load cases must start from the nonlinear analysis of the final stiffness of each cracked analysis case. And we are also going to take the opportunity to change the modal analysis so that this modal analysis can start from this nonlinear load case. Here we can make the change in the modal analysis. At this moment we have well defined the necessary elements to calculate the tables that will give us access to the stiffnesses and the displacements of the centers of mass. And we are going to run the model. It is important to point out that, but why are we applying the forces and loads at the top of the building, on the roof, and not on every story? Well, the truth is that a force applied at the top of the building is transmitted equally across all stories. And the geometric center of the top of the building is not the same in all stories. And the center of rigidity alters across all stories. A little bit, not a lot, but a little bit. On the other hand, this alteration is not dramatic because, for one, it is small, and additionally, we are also going to take into account the exact placement of the center of rigidity through an expression that we are going to apply. But it is normal that the center of rigidity will change its position because the stiffness of the elements is actually changing in height and the relative distribution is also distributed differently. And so it is something that we can later check to see how the centers of rigidity are varying across all the stories. Well, but this is just to tell you that we should be at ease with the fact that we are applying forces only on the top story. We are going to look at the tables that interest us. And we start with, for example, the results for the centers of mass and rigidity, which we will have to get again. And we are also going to look at the displacements. The assembled masses, the joints are also necessary, precisely because we need mass sums to calculate some of the ratios. And also the displacements of the centers of mass, which is basically the table that works for diaphragms, and that we are going to use to discover, in an initial phase, the rotations of each story and the displacements of each story, and by using the information, establish relative displacements between stories, which in a way, allow us to account for the stiffness of each story, or calculate the stiffness of each story. We are going to use Excel again. These tables to Excel, that is what we are going to do. And we are going to, before making a copy, apply some filters to the ETABS tables. We are going to sort the output cases so that it is possible to separate the load cases more easily. We could do it in Excel, but here it is shown that it is also possible to do it directly in ETABS. It is very easy. And now yes, we are going to export the tables. At this point, our objective is to determine the ratios in the first table that will allow us to calculate the L's values per story. The assembled masses at each floor per story are important. We apply a filter, remove the unnecessary values, or rather, bring in the values from the joints. These z-axis values are exactly the values for the polar moment of inertia of the masses. We are going to take the square root of the z-axis value divided by the assembled mass at each story, which is the same whether it is in x or y. And we obtain these L's factors, which require a correction. This is because in the ETABS table, for polar moments of inertia, the results are reported in tons and not kilograms. Therefore, there is a correction factor that must be applied to obtain the final factors. Thus, the L's factors are calculated, which is the easiest part of the calculation. Now we are going to calculate the other elements and factors required for the torsional stiffness calculation. To determine the torsional stiffness, we will first remove some unnecessary columns. We are going to separate the tables between the moment and torsion forces and the horizontal displacement forces in both directions. So, we must perform a separation. Now we have three distinct tables here. We expand the cells a bit and give them names. We will begin defining the formulas we need to apply to calculate the values we want. We will also remove some unnecessary columns here as well. Alright, now it is easier. We are going to add some additional data, some additional columns. For example, the torsional stiffness is the first one we want to calculate. This depends on the moment we are applying, which is the value we previously defined. One E6 divided by another value which is, basically, the rotation difference between the two stories. In other words, we use the rotation differences between two sequential stories to get the relative rotation. And we automatically obtain the torsional stiffness very easily. Now we are going to try to do the same for the translational displacements and calculate the stiffness. Taking into account the applied horizontal force and the relative displacement in the two horizontal directions. These displacements we are calculating are displacements at the center of mass and not displacements at the center of stiffness. Therefore, we will have to make a slight adjustment. For rotation, it is not important, but for translations, it is indeed important. This is not the total stiffness value that we actually want to calculate, but we already have a simplified form. We are going to see the stiffness results calculated at the center of mass, which is not exactly what we are looking for. Once again, adjusting the formula here to give us the correct values. We will give it another name. Stiffness Fy. We will do the same for the stiffness in Fx using the same philosophy. But once again, remember that these are values associated with the displacements we measured at the center of mass, which is not exactly what we intend. What we want is to measure them at the centers of stiffness. So, we are going to remove some unnecessary columns again. We are preparing the necessary elements to calculate the displacements at the center of stiffness. That is, we are going to place the table of the centers of stiffness here. How will we do it? We are fundamentally going to create some additional variables. The displacements at the center of stiffness will be equal to the displacements at the center of mass, plus an eccentricity times the rotation in z. This eccentricity is the distance between the coordinates of the center of stiffness minus the coordinate of the center of mass. What we have here is exactly building the expression. The delta of the center of stiffness is basically the center of mass plus this eccentricity, which we will call E0x, times the rotation. The same then applies to the other coordinate in x. We are going to calculate our E0x now. We will insert a new column and calculate both E0x and E0y, which are necessary to then calculate the x and y contributions of the new displacement at the centers of stiffness. How do we do it? Very easily. The distance between the x and y coordinates of the center of stiffness minus the center of mass and the difference in x and y. This is the eccentricity we are considering. Then we also consider the YCR and the XCR using the expression we had below. Now we will set it equal to the displacement of the original center of mass plus the expression of E0x times the rotation in z. This is applied to all stories, and we do exactly the same for the other variable. We are creating the formula for the other direction. There is a small error here, a mistake I am resolving because the center values are in meters and I have to convert them to millimeters so that all values are in millimeters. But this correction is very easy to make and must be done in all cells. Now we are going to update the stiffnesses in the two translational directions, using not the initial displacements at the centers of mass, but the estimated displacements at the centers of stiffness for each story. We are going to see that there are some changes. At this point, we are in a position to calculate our Rx factor, which then has to be compared with the L's factor. We will take the ratio of the torsional stiffness divided by the lateral stiffness, the square root. That is, torsional stiffness over lateral stiffness. We will calculate this ratio for all stories, which clearly depends on both directions, x and y. We will do the same now for y across all stories. Now we are going to select the other factor and bring these values into our Excel sheet so that it is possible to calculate the ratio independently in both directions. We are going to see that this ratio must be less than 1, and we will verify it. As we can see, all stories in both directions are less than 1. The ratio allows us to verify this difference of less than 1, except on the first floor. The difference we have here is a 3% difference. The truth is that we believe this check, even with this one floor having a small 3% difference, should not limit us from considering it a system that is not torsionally flexible. In other words, these values represent a small difference that is occasionally insignificant. It is a very small difference occurring on only one floor. In global terms, it is a matter of engineering judgment, but we could accept that the system is not torsionally flexible. All values are below the value of 1, except for one floor where there is a small difference, and in general, we conclude it is not torsionally flexible. Well, now that we have verified that the structure is not torsionally flexible and is also not an inverted pendulum, we must determine what type of structural system we are talking about. We have several possibilities. It could be a frame system or a frame equivalent dual system. It could be a wall system or a wall equivalent dual system. The distinction between being a wall system or a frame system relates to a rule recommended by the Eurocode, which tells us the following. If the shear resistance of the structure is divided such that, for example, 65% of the resistance is held by the walls, then it is a wall structure. If, on the other hand, at least 65% of the shear resistance is held by the frame elements, then it is a frame structure. However, the code also tells us that in cases where it is not easy to work with structural resistance, since using the resistive values of elements is naturally much more difficult before the structural calculation, one can also use the values of the internal forces, the acting forces. This changes the rule slightly. If we have, for example, under seismic action, 65% or more of the forces being resisted by the walls, we classify it as a wall structure. If they are resisted by the frames, we classify it as a frame structure. There is still another possibility. Within the walls or frames, one can consider the question of being dual, mixed. Dual or not means that if the structure presents a predominance of walls or frames, predominance meaning greater than 50% but not reaching 65%, then it is considered a wall or frame system but is designated as dual. Another very interesting and important possibility regarding walls is that it can be a wall system, dual or not, but either coupled or uncoupled. The coupling of wall systems relates to another set of rules that we will discuss now. The concept of coupling between walls is such that, according to the code, coupling occurs if we have a 20% to 25% reduction in the moments at the base of the walls compared to when they function independently and uncoupled. In other words, by introducing coupling, a reduction of the moments at the base will occur. Let's see how this works. Imagine two independent walls on the left, close to each other and functioning and bending about their major axis. The global moment of this set of walls is the sum of the two moments. If we introduce coupling elements, our global moment now depends on the individual moments in each of these two walls, but also on a couple, a pair of axial forces, that contribute to the global moment as well. The code tells us that looking only at the moment components, these coupling beams should be capable of reducing the individual moments by at least 25%. If this condition is guaranteed, we can say the system is coupled. If not, it is uncoupled. Now let's look at what we are going to do in our flowchart. Fundamentally, we have to do two things. One is to classify the structure as a wall or frame system. As noted earlier, to do this it is important to calculate the distribution of forces from a seismic analysis between the walls and the frames. After determining the type of structure, we see if it is necessary, in the case of walls, to classify them as coupled or uncoupled. A very important question is, what type of seismic calculation will we use for these classification forces? We are going to use the equivalent lateral force method, LFM, because it allows us to obtain the base reactions of the building in a very easy and balanced way. Since we are dealing with a relative classification, meaning it depends on the relative forces between walls and frames, the question arises, is the magnitude of the earthquake very important? Generally, no. It is not very important. I would say the most important thing is to follow the seismic definitions, but specifically the vertical distribution of the seismic forces so that it resembles a normal earthquake as much as possible. Therefore, while we will use the seismic definitions I will explain, the maximum reference magnitude applied during this classification stage is not critical. Another very important question is defining which model will be subjected to this earthquake, the primary structure or the global structure. And also, with what type of element stiffness, the 50% reduction. First, the stiffness level is not vital. We could use 100% or 50%, but we will use what is already defined in our model. However, whether we use the global model or the primary structure model is a point we want to make very clear. It should be the primary structure. The objective is simple. Since classification as a wall or frame system, even if dual, implies a 50% contribution from one of these systems. If we used a global calculation system, the secondary elements might absorb base forces in a way that prevents either the frames or walls from reaching a contribution higher than 50%. For the sake of consistency and doing it correctly, it seems more accurate to perform this check with the primary system. So, we will use the primary model we already know as the basis for our seismic calculation. We had defined our ETABS model with 50% stiffnesses. We will use a modal analysis to determine the fundamental periods which the structure uses to determine the seismic load. We could choose either the primary or global structure for the modal analysis, but we will choose the global one, as it seems most suitable to represent the three-dimensional global behavior of the structure and ensures we are closer to the actual natural frequencies and periods. Now we are going to apply this equivalent static load in the model. We unlock the model and define our load. In the load pattern, the name we will give it is LFM primary because we are applying the equivalent static seismic load to the primary structure. We define it as a seismic load following the Eurocode. Using the automated lateral load feature, we are going to modify the lateral load to configure the parameters. One is the eccentricities. It is possible to automatically account for eccentricities in the application of forces in the two independent directions, but we will not use that here because our goal is not design, but simply comparison within our model. We can remove these eccentricity options. We only have two directions to apply the load. We can also decide whether the vibration modes are calculated internally according to the spectrum or if we define them ourselves. For the seismic definition, which in our case is a ground type B, type 1 spectrum, zone 1.3, we must enter the AG value. Specifically, 1.5 AG over G, which in the program must be entered as the value divided by G. Before doing that, we can define and choose the national annex we want to use. Afterward, if there is a need, we can configure other values manually. We take full advantage of the automatic national annex definitions the program allows, and then, if necessary, we can simply change any desired factors. As I mentioned before, the specific definition is not super important. One additional note, in the story range area, we can apply this seismic load not just to all floors, but only to some. This is particularly practical when we have basement walls, where it may be useful to apply the earthquake only to the upper floors above the basement walls. Well, this is the definition we made for our seismic loads, the earthquake in both directions. What we are also going to do now is define the modal analysis used to determine the principal periods that the equivalent lateral force calculation will utilize. For this, we will use the primary structure and perform the calculation now. Here we see the load cases we want to run. Only the modal and the equivalent static load, and we run the model. It will take a few seconds. We will wait a moment to see the results. It always takes a few seconds before it is possible to evaluate the shear values in the structure. We are practically finished. The modal analysis modes are done as well. And now, the calculation is complete. Now that the model is calculated, the first step we take is to look at our base reactions to get a global idea of the magnitude of the reactions we are obtaining. To do this, we export the reactions table and look at the reactions in X and Y for both directions. the two steps of the equivalent static load case. The thing is, while these values are very interesting globally, they do not help us discover the distribution relationships. That is, the distribution of forces between the walls and the frames. Therefore, we need something more. Another important point to explain is that base reactions might not be useful if we have basements, as we wouldn't be interested in the results at the basement level but rather at the upper floor levels. To do this, we are going to use the concept of section cuts, and we will also use groups to obtain independent results for walls and frames. We have already defined some groups, and we can see the distinction between walls and frames in them. We are going to define a section cut. Actually, two section cuts. One for the global structure and another for the wall structure. This way, we can determine the relationship between the walls and frames. The first is defined using a quadrilateral established by 4 points. These 4 points will have a spatial orientation defined by the right-hand rule, providing a section cut orientation vector. We are currently setting it up so the section cut faces upward. If we want the results at the joints below, we must give the section cut a negative orientation. We also need to locate it not exactly at the joints where we want the result, but slightly higher, within the elements that will be intersected by the section cut. I will leave the negative value for this negative z-axis because the forces we want are at the joints below. This is the relationship we are going to establish. Let's accept this section cut. Now we will look at the results. We will define the other section cut in the same way, but specifically for the walls. It is exactly the same as the previous section cut. While the previous one is somewhat equal to the base shears, as a rule, we should create both independently so we know exactly where each section cut is located. We repeat the entire process, with the difference that the group assigned here is the wall group. Now we are in a position to export the tables and explore the results. We export the section cut results. Now we can see the distinction for both groups regarding the seismic forces in both directions, step 1 and step 2. Aggregating to Excel, we can easily calculate the ratio of the total forces over, for example, the wall forces over total forces. In both directions. We see that in the x direction, we have an 84% contribution from the walls, and in the y direction, we have 96%. This means it is clearly a wall structure. We don't even need to discuss whether they are dual systems or if there are different wall types, because the value is significantly higher than 65%. Now the question is it coupled or uncoupled? We are back in the model, and what we want to do now is verify if it is a coupled or uncoupled wall structure. First, we will look only at the walls by selecting the wall group. Here we have the calculated results for our walls in terms of global moments and the moments in each individual wall. We are going to assign labels that will help us integrate the results for each specific wall zone. For example, in this case, we will use P1 and use this label to globally integrate the moment of these two walls.
we will look at the global moment of this set in the y direction. Let's change the text size a bit. Here we clearly see the result of the total moment of this set at the base. We can note in our Excel sheet that the total moment here is 39,487.6 kilonewtons meters. This is the global moment, and now the goal is to look at the isolated individual moments of each of these walls. To do this, we will assign two distinct labels. We keep P1 and use another, P2. We follow the same process and get two different values, M1 and M2, which are much smaller. Now we have those two moments. I will also show you the axial forces in the walls. And we see that we have two almost symmetrical axial forces, clearly creating a couple in our wall system. Now what we have to do is calculate the magnitude of this couple. Essentially, we subtract the sum of the independent moments from the global moment to find the value of the moment due to the couple. Our ratio of the reduction in individual moment due to coupling can be calculated as the moment of the couple divided by the global moment. This gives us an idea of how much reduction occurred in the individual wall moments. Why? Because we are assuming that, globally, the moments would have to be the same. Without coupling, ignoring that stiffness might differ slightly, this total global moment would have to be distributed between the two walls. Since it isn't, because we have coupling, the individual moments M1 and M2 are much smaller. The reduction we achieved was due to the axial couple, which clearly indicates the degree of coupling. The larger the couple, the greater the reduction of individual moments in each wall. Now we will repeat the procedure for the central core. An important note, when we look at the forces, the directions of the moments depend on the predominant length of the wall that is labeled.
So, the goal here is to study the coupling of this C-shaped core with the two linear walls. At this moment, we are assigning the same labels to all elements so that we can immediately estimate the global moment in one direction. Here, we have a value of 134,566 kilonewton meters. Let's update the values, 134,566. Now we are going to calculate M1 for the other two independently, using new labels to separately calculate the C-shape and the other two small walls connected to it by beams. We assign P4 to the walls now, leaving us with P4 and P3. We see that in the area of the linear walls, we have a moment, which we will call M1, of 21,614.7. The other one is different because, as I mentioned, the local axes have changed. This is because the program uses the local axes of the most predominant direction, the longest length, so we have to swap it. Here, we use the global moment of 5,622. By performing exactly the same type of calculation, we arrive at a reduction of 80% in this core, that is, in these walls. This means we clearly have an objective and well-defined coupling in our structure. We have one more wall that will not be coupled, but in our case, the majority of the walls are coupled. Specifically, The first two walls are the most important in the y direction, which is what we are trying to classify. In the other direction, the wall does not function as a wall in the y direction. Therefore, in the y direction, the structure is clearly classified as a coupled wall system. To finalize this part, we have now discovered the two main paths of our flowchart. In the y direction, we know it is a coupled wall system, and in the x direction, we know it is an uncoupled wall system, normal walls. In the next steps, we will calculate other factors, such as kW and other important aspects like regularity and elevation, which we will see shortly. Now we need to calculate another factor, the kW factor, which will influence our behavior factor. We can look at the flowchart to see the influence of the kW calculation. In all calculation lines, depending on the structural system classification, this factor can reduce the global behavior factor and determines to what extent that occurs. It depends heavily on the walls. If the walls of the building do not have sufficient slenderness, meaning they have a relationship between total height and plan length, such that they have too much inertia in the major direction, or the walls are very squat, then they might not have dissipative capacity. Eurocode 8 recommends a reduction factor that varies between 0.5 and 1. It uses a very simple expression to calculate this factor. It is 1.0 for frame systems or frame-equivalent dual systems, and it has an expression depending on an alpha-0 factor for wall systems or wall-equivalent dual systems. This alpha-0 factor is basically the ratio between the total height of the walls and their length in plan. We can calculate this as a summation of all walls in the building, or we can look at the least slender wall. This is usually easy to identify. If all walls have the same height, it is very easy to see which one is the least slender. If this wall yields a factor of 1.0, meaning the kW value is 1.0, then we do not need to calculate the sum of the contributions from all the other walls. In our case, the least slender wall has a height of 41.4 meters and a plan length of 7.42 meters. The total factor we calculated is 5.57. Since the expression results in a value greater than 2, it means the kW value is 1.0. We conclude from our flowchart that there is no need to reduce the behavior factor we previously calculated in either direction. Another very important topic is checking the regularity and elevation of the building. This topic arises because our flowchart shows that for any structural system direction, there is an important requirement, a 20% reduction in the behavior factor if the building is not regular in elevation. Let's look at how Eurocode defines regularity and elevation. There are some fundamental conditions. First, all structural systems intended to resist seismic actions and lateral loads, such as walls, cores, and frames, must be continuous in height. This is a fundamental condition, and our building clearly meets it. Even in situations where a building has setbacks in the facades, the elements we are talking about must maintain their continuity until the level of the setback. Another very important aspect is that the lateral stiffness of each story and the mass distribution over the height must not have abrupt changes. There must be continuity in the stiffness and mass variations of our building. Looking at our building, we recognize that the structural elements do not have significant section changes, and those that do, like the central columns, have very small variations. Furthermore, the changes in terms of mass are also insignificant, occurring only at the roof level due to the reduction in live loads and other dead loads. It does not appear that we have a building with any abrupt changes in stiffness or mass over its height. The third important aspect is that there should not be changes in the overstrength of the building at each story between adjacent floors. The elements we design at each story will certainly have a certain overstrength factor relative to the design forces, and the requirement is that we do not have overly overstrength elements on floors that are adjacent, ensuring this factor is not wildly different between adjacent levels. Now, let's talk about the check we are going to perform on our building. With these criteria we just discussed, we could say that we don't really need any further checks and that, in general, our building is regular in height. However, for academic purposes, it is important to see how we can very quickly justify this continuity or regularity in a simple way. Taking advantage of our previous work, where we calculated important tables for mass per story and bending stiffness in each direction for each floor, we can perform some additional calculations. Looking at these previous elements, starting for example with the bending stiffness at each floor, we can organize this information into a small bar chart. We can see from right to left the floors rising in height with the two different directions shown in blue and red. And we see that we truly have continuity. That is, there are changes, as expected, because the stiffness will naturally change from the base, due to the total fixity of all structural elements, until the point where this fixity is no longer as significant and the stiffness remains more or less constant at each story. However, there is no fundamental aspect visible that would point to an unnecessary or exaggerated change in stiffness beyond what is normal for a wall or frame building. In wall structures specifically, this is more noticeable. Looking at these two charts, we can clearly conclude that from the standpoint of story-to-story stiffness variation, lateral bending stiffness per story, this is not a reason to disqualify the structure as regular in height. Let's also look at the masses. Regarding the masses, we look at another table we calculated previously and clearly see the effect I mentioned earlier. The masses are practically constant across all floors. There is a small difference at the top roof level, which is related to changes in live loads and other dead loads in that area of the building. With this, we can conclude that since the structure has an acceptable variation in mass and an acceptable variation in lateral bending stiffness, and since no special overstrength is expected, given the geometry and design intent, it is very clear to us that the structure is regular in height. There is another topic I forgot to mention when we looked at the height stiffness table. There are small differences, specifically at the roof, where we see a slight increase in story stiffness because we have a perimeter beam that wasn't present on other floors. While this is true, one must apply engineering judgment to ensure we aren't looking at stiffness changes with millimeter precision. These are qualitative values that can be observed and verified quantitatively, but engineering judgment means we shouldn't just look at numbers and seek exact limits to satisfy. We simply look at the behavior of both mass and stiffness criteria and remain satisfied with results that appear reasonable. This is the case for this building's regularity in height. An additional point I should mention: these abrupt changes that shouldn't be found in the structure are one aspect, but the Eurocode also tells us that the changes we find should generally be in a descending direction. That is, as we go up the floors, the stiffness and masses should decrease, and these changes should not be abrupt. Even if changes aren't abrupt, if the stiffness or mass starts to increase as we go up the floors, then regularity in height is no longer verified. It is not just about having smooth transitions. It is about ensuring we primarily have decreases rather than increases. We can have a small increase, as occurred at the roof level, but we should not have significant increases. That concludes the topic of regularity in height. Now that we have verified the building is regular in height, it is time to look at other aspects of our workflow and decision-making. What other data do we need to finally configure our behavior factor? We have seen that in the Y direction, our structure is classified as coupled walls. We see clearly here that the classification and calculation of the behavior factor depends on Kw and another factor, alpha U over alpha 1, which we must calculate. In the X direction, for uncoupled walls, we do not need the alpha U over alpha 1 dependency, only the Kw factor is required. In the abstract, we can say right now that for the chosen ductility class, medium ductility, DCM uncoupled walls have a behavior factor of 3.0. But as I mentioned, for coupled walls in the Y direction, we must calculate the alpha U over alpha 1 factor. This calculation can be done using two methods. One is to perform a pushover analysis as indicated by the Eurocode to explicitly calculate aspects of the building's dissipative capacity, providing some flexibility in how we configure this factor and calculate our final behavior factor. The other method is a simplified method that depends on the typology of the structural system resisting seismic forces and other aspects of the building's morphology and geometry. We are choosing the simplified method for the sake of simplicity. This factor can help us amplify the behavior factor, and it depends on regularity in plan. To calculate this factor using the simplified method, we use a table well described in the Eurocode. Depending on the structural system and geometric typology, if we have a building that is regular in plan, we use the simplified factor directly. If the structure is not regular in plan, we must take the average of 1.0 and the factor from the table, resulting in a reduced factor. This means we cannot amplify the behavior factor as much if the structure is not regular in plan. Now let's look at the conditions to classify the structure as regular in plan. The Eurocode indicates 2 points we must verify, 4.1a and 4.1b, which relate to concepts we visited earlier. The first condition is that E0x, in both directions, must be less than or equal to 30% of the Rx coefficient. The other condition is that Rx must be greater than or equal to Ls. We saw these earlier when checking if the system was torsionally flexible. We calculated both Rx and Ls. As a reminder, Rx was the square root of the torsional stiffness divided by the bending stiffness for each story. On the other hand, the L's factor was basically a radius of gyration of the masses, the square root of the polar moment of inertia of the masses with respect to the center of mass, divided by the sum of the total masses of each story. We already have these two factors, and we are familiar with their meanings. The condition 4.1a, E0x being less than 30% of Rx, must be checked in both x and y directions. Basically, this tells us that the eccentricity between the center of stiffness and the center of mass must be less than 30% of the Rx coefficient. Why? Because the Rx coefficient gives us an idea, measured as a length, of the radius of gyration related to the torsional capacity of the structure. If we have a very large eccentricity, a large distance between the center of mass and the center of stiffness, the Eurocode considers that if the proportion of this distance cannot satisfy this expression, we should not consider the structure regular in plan. Being regular in plan allows for better behavior regarding torsion and the torsional capacity of the building. So, what we are going to do is recover the values we had previously. We had even calculated these eccentricities at the moment we had to transpose the bending stiffnesses from the centers of mass to the centers of stiffness. Alright, let's open our Excel sheets and create two new columns to begin verifying these factors. We will start by looking at the expression E0x less than 30% of Rx because we are going to check it in both directions. Basically, we're going to directly include the eccentricities calculated earlier related to the Rx factor. And we will also directly include the 0.3 factor so that the expression is comparable to 1. Below a value of 1 in these expressions, we are fine. Above that value, we are not. In that case, we do not satisfy the Eurocode expression. The question then arises, do we have to check these in independent directions? That is, can the structure be regular in plan in two independent directions? We don't believe so. It is enough for it to be non-regular in one direction, and that is exactly what happens here. Why? Because if these checks relate to torsional aspects, it makes no sense to assume independence in how we verify regularity in plan for x and y. In our particular case, we see that it is not regular in plan because the ratio in y is greater than 1. This means it does not satisfy the inequality E0x is less than or equal to 0.3 times Rx. So let's look at the influence this has on our behavior factor. In the y direction, we have a coupled wall system, so the alpha u over alpha 1 ratio is 1.2. But, as we mentioned, since the structure is not regular, we do something to reduce this value. We take the average with the value 1.0. Therefore, the final value for alpha u over alpha 1 is 1.2 plus 1.0 divided by 2, which gives us 1.1. This is the final factor that allows us to calculate our behavior factor. 3 times the alpha u over alpha 1 factor of 1.1 times our kw factor of 1. It is very easy to do the math, and we now have two behavior factors for the two directions. We have performed quite a few checks to finally arrive at the behavior factors. To make it clear, let's look at the paths we took to reach the final results. Assuming we have medium ductility class, DCM, we have a behavior factor of 3.3 in the y direction and 3.0 in the x direction. At this point, we have completed one of the most important aspects of these checks before starting the structural calculation. We have left one quite important aspect for the end, verifying that our secondary and primary structures respect the rules imposed by the Eurocode. The main rule, in addition to all the others we have verified so far, states that the contribution of the secondary elements to the bending and shear stiffness in all stories of our structure must be less than 15% of the stiffness of the primary structure. This means that if we initially chose a very broad set of secondary elements, it is possible that by this phase, after checking regularity in plan, regularity in height, and other rules, we might find the secondary element's stiffness contribution is greater than 15% of the primary structure. So, the question is how we are going to check this in our building. We have seen many academic and professional examples where one of the checks performed is to calculate the base shear and separate it between the primary and secondary structures. This is a possibility, but from our perspective, it might not be the best way to do it, and I will explain why. For example, if this ratio is very close to 15% at the base, and we know that in wall or wall-equivalent dual structures where the walls have a very high predominance of stiffness, wall stiffness clearly decreases with height. It is common for structures near that 15% limit at the base to see the secondary element's contribution increase proportionally to the primary elements as we go up, assuming the geometric proportion of elements remains the same. Therefore, guaranteeing this proportion only at the base does not seem entirely adequate to us. It works for an initial estimate, and if the value is very low, like 3% or 5%, there would be no problem. But a value close to 15% would not make me comfortable. What other possibilities do we have? We could, for example, check the shears at every floor and the relative shears between the primary and secondary structures. This would require us to create section cuts at every story. Another possibility, which we prefer because it is simpler, is to simply consider the difference in drifts, the relative displacements between floors, for the same load case, comparing a structure that functions only with the primary system against a structure that functions with both primary and secondary systems. An important aspect is that the checks we perform are independent by story. It is natural that if we based our checks on shears or story drifts, we would get different results per floor. If the 15% limit is met on some floors but not on others, it is an engineering decision for the designer to justify why they considered the distinction between primary and secondary structures appropriate. We will keep this philosophy regarding drifts and story displacements in mind and see how to proceed. Let's look at how to calculate the influence of secondary elements on the structure's resistance in our model. We must consider how to define the action we will use for the comparison. It should be a horizontal action, preferably seismic. Why not use a response spectrum analysis? The truth is that we are talking about two structures with totally different stiffness configurations. One we call crack stiffness, including primary and secondary elements, and the other being only the primary structure. If we used a response spectrum, it would be based on modal analyses reporting different stiffnesses, different fundamental periods, different frequencies, and different accelerations on the spectrum. We wouldn't truly be comparing two actions with the exact same magnitude and distribution. What we need is an action that, while perhaps not perfect in terms of seismic definition, has the same magnitude and vertical distribution when applied to the primary structure versus the primary plus secondary structure to allow for a fair comparison. Details regarding the behavior coefficient are not important here either, because the key is having the same action applied to two different structures so that the contributions of the primary and secondary structures are comparable as a percentage. Therefore, to be clear, what we want to ensure is that the stiffness of the secondary structure contributes less than 15% to the stiffness of the global structure. To achieve this, we are going to compare the story drifts or displacements for both scenarios. We will now define our equivalent static action. We previously had one set up for the primary structure, which we see here as LFM primary. I see that, by mistake, it was not starting from a nonlinear case. I am going to correct that now, although it does not influence the calculations we performed earlier. This correction is made, and now we will create a copy for the global structure. It should not start from the primary structure but from the crack stiffness model, which was our global structure. This ensures we have the exact same action acting on two different structures. One that is primary only and another that is primary plus secondary, allowing us to identify the contribution of the secondary elements. In our analysis tree, we can see the load cases dependent on our global stiffness. Here we see the equivalent static load case for the global earthquake, and, below it, the equivalent seismic action for the primary structure. With the load cases prepared, we will run the analysis. The program will now calculate our seismic actions using equivalent static loads. The goal is to access the tables in a few seconds that will provide the exact story drifts. An important point we will see is that the drifts we obtain can be maximum, minimum, or average values. We will see in detail how to distinguish between these values and how to access them in the ETABS tables. The analysis is complete. We will access our table under displacements, specifically the story max over average drifts. This is the last table. We select the relevant load cases, the seismic load on the primary structure and on the global structure. We expect to see not just a single drift per floor, but maximum and average values, and we will have to decide which ones to use. An important aspect is that when we perform an equivalent static seismic load, two directions are calculated. The program divides these into direction 1 and 2, X and Y, and reports them in steps. Therefore, for the X direction, the reported drift direction and step 1 represent the load acting in the X direction. It can be a bit confusing, but we are currently separating the tables for the global and primary structures, focusing on the earthquake applied in the X direction, and the results that interest us in the X direction as well. Giving these different names to make them easier to understand. We will remove some unnecessary elements. We are now ready to generate columns for the ratios, one related to average drifts and another to maximum drifts. We see that we have done this for the averages, and now we will do it for the maximums. We notice that, particularly on the upper floors, the contribution coefficients of the secondary elements are slightly higher than 15%. However, up to the 8th floor, we are safe as they are all below 15%. There is a small contribution in this X direction that peaks at around 3% over the limit, which brings the check into question. We will also look at the other direction. For the earthquake in the other direction, we follow the exact same steps, export the table or filter by direction, in this case, direction 2, step 2, and the Y direction, and reorganize the Excel tables in the same way. Once again, it is important to observe, as we saw with the previous numbers, that there is different behavior as we move up in height. In the Y direction, the values are not as severe. Even on the top floor, we are right at the 15% maximum, and generally, the entire building has a secondary element contribution of less than 15%, as we initially hoped. In cases where doubts arise, we are making the decision now to accept the distribution of secondary and primary elements. We accept that this distinction, where we find values between 16% and 17% on the upper floors, is not significant enough to characterize the whole building or prevent us from classifying the structure as primary and secondary in an acceptable way. We will accept it. On the other hand, It is very important to tell you that if these numbers forced us to revise the distribution between secondary and primary elements, some of the checks we performed earlier would have to be repeated, not necessarily all of them, but specifically those that help classify the structural system. This is a crucial point to consider, because arriving at this stage only to conclude that the secondary elements do not comply with the Eurocode 8 rule regarding the 15% contribution limit would force us to redo a significant amount of work. Therefore, one must be quite careful and not be too optimistic about the number of elements categorized as secondary. This concludes the first part of the webinar. We have followed all the steps to characterize the structure, define its behavior, determine its behavior coefficient, define its structural system, perceive whether the structure has torsional susceptibilities, and verify that the distinction between the primary and secondary structure is correctly defined. We now end this first section and move into a Q&A phase to dialogue with the trainees.